Now you've already looked at symmetries and reflecting about x-axis, y-axis. Now let's apply that to some problems. When we're given a graph and we're going to do some reflecting, what we really want to do is focus on the kind of key points of the graph. And in this case, since they're all line segments, let's look at where the endpoints of each line segment are, the vertices of this graph. Y equals negative f of x. Now remember what this is. F of x represents our y value, so we're saying negative of these y values. Whatever the y values were, we're going to change the sign of them. We're going to make them opposite. So here's a point. The x value is staying the same. At negative 2, it was at negative 1, but it's going to flip over. It's reflecting about the x-axis. This was at positive 1. Now it's going to be at negative 1. Positive 1 is also going to be at negative 1. Again, the same x values. And then 0 would just stay 0. And at this point, you can just connect the dots. And that equals y equals negative f of x. There's our graph. F of negative x. Remember what this does is it reflects it about the y-axis this time. So if I wanted to get negative 2, this value, what I do is end up plugging in positive 2. So when x is positive 2, I'm going to get this value, and it'll be negative 1. And you can kind of think of it here. If we were just looking at our values, negative 2, negative 1, 0, 1, 2. Actually, I don't really care about the negative 1 part. I plug in 2, and I get f of negative 2, and f of negative 2 is negative 1. F of negative 1 is 0. F of 0 stays at 1. F of 1 is 1. And f of 2 would be 0. So I could just plot those points. At negative 2, it's a 0. At negative 1, it's 1. At 0, it's 1. At 1, it is 0. So we have a graph that looks like this. Again, what is that? That's a reflection about the y-axis. Now, what does the absolute value do? If the graph is above the x-axis already, it doesn't do anything. So, or if it's 0. So that first part does not change at all. What does it do to this part that's below? It's going to reflect it above the x-axis. And there's a couple examples on dealing with that. Let's take a look at this type of problem. Now, first, on the first one, we know our vertex is going to be at negative 1, 3. We have an axis of symmetry at x equals negative 1. So we have negative 1, 3. And remember, since this coefficient here is 2, it's going to be, instead of going up 1 and over 1, it's going to go up 1 and over 1 and up 2. Over 1 up 2. And we could plug in 0 and we would get the same value. And I don't have enough here to graph anymore, but that's okay. Our axis of symmetry is x equals negative 1. What is this doing? This time we have a vertex that's going to be at 3, negative 1. 3, negative 1. And one way you could do is plot some values here. Let's say I plugged in y equals 0, then I'd get x is 5. Or y equals negative 2, and I'd get x is 5. What do you notice about these graphs? Well, the x and y values are switched. What did we talk about last time? When you switch about the x and y values, x and y values are switched. It's going to be a reflection about the line y equals x. So every single point that's on this graph, let's take a look at this one here. This one is negative 2, 5. We have negative 1, 3. And then this last one would be 0, 5. Over here, we get 5, 0. 5, negative 2, and 3 comma negative 1. What do you notice about all those? The x and y's are switched, and that's exactly what was done here. Oh, I didn't write my axis of symmetry on this one. Axis of symmetry, this time the axis of symmetry is a horizontal line, so that's going to be at y equals negative 1. Let's look at the next piece. Definition, axis of symmetry. When you fold the graph about the line, the two halves are the same. So you think about that. If I take and I fold this in that previous example in the parabola, if I fold it about the axis of symmetry, both sides match up. And that's our whole idea when we find the axis of symmetry, by averaging the midpoint or finding the midpoint of two x values. For example, the zeros. All points not on the axis match to a pair point. They all have a matching pair. That's when we graph our symmetric point. The axis, now here's more of a formal, it's not totally formal, but that's okay. The axis of symmetry is the perpendicular bisector of all those matching pair, the pair points. Just like when we found the axis of symmetry for the parabola, we would find our zeros and average them together. You can do the same thing always for any axis of symmetry. This will always work. An example of this, although we don't use it unless we prove it, what does x equal? Negative b over 2a. Now we're going to talk about a point of symmetry. The graph is rotated 180 degrees about that point. The two halves are the same. All the points, all the other points besides that one, match to a pair point. So a little more formal is the point of symmetry is the midpoint of all the pair points. Let's see about applying this and finding an example, and we'll look at what's happening here. What I want to do is sketch this graph, find the zeros degree if it's positive or negative. Now, if we look at factor by grouping, find the zeros, we'll have an x minus 3 here and an x minus 2 there, so that's not going to work, so we're going to need to use synthetic division. What number do I want to try? The first thing I want to do, actually, that's 3. I want to check to see, does 1 work? Add all the coefficients. Do those equal 0? Yes, it does, so 1 works. So let's take it out. So we get x squared minus 2x minus 4 equals 0. Now, is that factorable? No, there's nothing that multiplies to give us negative 4 that adds to give us negative 2. So we can use a quadratic formula. 2 plus or minus square root of 4 minus 4 times 1 times negative 4 all over 2 times 1. So we have 2 plus or minus 4 plus 16 square root of 20 over 2. So 2 plus or minus 2 root 5 over 2. So we have 1 plus or minus root 5. Now I showed you how to do that before in terms of estimating this. This is approximately equal to 2.2 when we're going to sketch our graph here. Let's take a look. 1, 2, 3, 1, 2, negative 3. All right, so we have a 0 at 1. And if we say 1 plus 2.2, we'll have it about 3.2. And then 1 minus 2.2, it'll be about negative 1.2. The degree is 3, and it's a positive graph. So from this last 0, it's going up. Each 0 occurred one time. Estimate the point of symmetry. Where do you think there's 180 degrees and both sides match up? Now my graph's not perfect, but if how did we get this point? It was 1 plus root 5 and then 1 minus root 5. Well, we have 2 points there, and this is the midpoint. That is 1, x equals 1, or in other words, 1 comma 0 in this part. There's some things I need to go over with you. This is called the local minimum. We're going to be using these words. Here's a local maximum. This graph right in this section here is called concave up. And this section from the point of symmetry over is called concave down. A standard way to think of it, if you kind of extend the graph out, a concave up, it could be called holding water, and concave down, spilling water. It's not a perfect example, but it'll have to work for right now. Now, here's a rule for this, the point of symmetry for a cubic equation. Well, remember that the quadratic equation is x equals negative b over 2a. Similarly, in this one, it's going to be negative b over 3a. We're just going to use this. We don't have the knowledge to prove this, and that's okay for right now. Now, one question that would be a good one that some people are thinking about, and that is, what if it was a fourth degree equation, a quartic equation? Does the rule extend to that one? And the answer is no. All right, so now let's try to find this. It says find the point of symmetry. Here's a cubic equation. We're going to say x equals negative b over 3a. In this case, b is 15 and a is negative 1. So we have negative 15 over 3 times negative 1. So we get negative 15 over negative 3, and that gives us positive 5. Now, how do we find the point? We have to find x and y. If we know x is 5, we need to find f of 5. So we have negative 5 cubed plus 5 times 5 squared minus 48 times 5 plus 45. So this is negative 125 plus 15 times 25, which would be 375, minus 240 plus 45. Let's see, this is going to give us negative 300, these two together, 65, and then add it with 375 is 10, so this will give us 55. So our point would be 5, 55. The function has a local min at 2, 1. At what point does the local max occur? Well, this is a negative cubic, and it's going to look something like this. This point of symmetry right here is 5, 55. And we're told that the minimum is 2, 1. Well, we can see that's going to be right here, 2, 1. Where is the max? Well, if this is at the midpoint of those values, one way to do it is just count how high do I have to go here and how far to the right, and then I want to do those exact same values going over. And I can think of this just like slope. So let's write this down, delta x. The change in x here is going to be 5 minus 2 or 3, and the change in y is going to be 55 minus 1 or 54. So if I take 2 and I add 3 to it, I get my 5, and I take the 1 and I add 54 to it, and I get my 55. Now I need to do the exact same thing to get my local max. So but this time I'm going to start at my point of symmetry. So the max will be the x value, is going to be the x value here, my point of symmetry, and I'm going to be adding it since I'm going right. So 5 plus 3, and that gives me my 8. And y will be 55 plus 54, which would be 109. So my local max here would be 8, 109. While the video is getting a little long, it's at 15 minutes, let me show one more example and to see if that helps. So I want to find the local min, point of symmetry, local max. Here's a hint, we don't know where to begin, sketch this graph. So the first thing I want to do is I want to factor this out. So I have negative x, and then I have x squared plus 6x plus 9, which means negative x times x plus 3 squared. It's a degree 3 equation. It's negative, and my zeros are x equals 0 and negative 3, but negative 3 is a double root. This is going to be important for this particular problem. So when I'm sketching this, I have 0, and then I have a negative 3, and it's negative, so it's coming down at the 0, and it goes up, and it bounces off at the negative 3, and then goes up. The only way we're going to be able to figure out all three of these things without knowing some other type of math is the fact that one of them is given to us. When we look at this, what is that point? That's the minimum in this area. Here is our local min, and so that point is just negative 3, 0. How do I find my point of symmetry? I'm going to plug in, I'm going to say x equals negative b, so it's negative of negative 6 over 3 times negative 1. So 6 over negative 3 would be negative 2. Plug in negative 2, so we're going to say y of negative 2, negative of negative 2 cubed, minus 6 times negative 2 squared, minus 9 times negative 2. So that would be negative 8, and a negative of that's positive 8. And then positive 4 times negative 6 is negative 24. And then plus 18, and that'll give us 2. So this point here is 2, 2. How do I go about finding my local max in this one? Well, my change in x is going to be 2 minus negative 3. No, I'm sorry, I wrote this as 2. It's negative 2 minus negative 3, and that gives us positive 1. And then the change in y will be 2 minus 0, or 2. That's going to be, I'm going to be going up 2 and right 1, so I'm going to go up 2 and right 1 again. So my x value is going to start at the negative 2, and it's going to add 1. So that gives us negative 1. Y value is going to add 2 to it, so it gives us positive 4. So we'll have negative 1, 4, and that'll be my max, and that is it.